Hello everybody, welcome to this new episode of Probabilistic Robotics. Topic of today will be a mini recap of epipolar geometry on the unit sphere, and this you can read it on the slides as well. I don't know whether it's a recap or it's a new information for you, but today we will add to our toolbox some additional instrument, let's say. Okay, now I'd like you to participate actively to this lesson, and then before going to the next slide, I will just stand still and ask you to try to derive certain things on yourself, by yourself, okay? So that it goes through you, and I think it's a good idea. All right, now let's talk about lines. No? First thing, why lines? Lines, because we're talking about projective geometry, which means geometry that maps 3D onto 2D, and normally this mapping is consistent along a line, meaning that if you have a camera image, all points in the space that lie along a specific line that passes through the camera center will be mapped in the same point of the image. Right? So one point of the image maps to a line in the space. Agreed? Very good. And so we are interested in representing lines. Okay, now lines might have a gazillion lines in the space, right? Might have different representations if you want. We don't care about which one we choose, but I find it very intuitive for a robotics to speak about lines in this form. So I describe a line as a point on the line, any point on the line, let's call it P0, and I could describe having this point, all lines passing through this point as this point plus a certain direction vector which is multiplied by a scalar quantity. So it's like I have a unit vector which is applied to a certain specific point in the space, which I call P0, and then I have a direction vector which is a unit vector that describes me the direction, and then I could describe every single point of the line by moving this S0, this assissa, along forth and back the direction. It's like magnifying the direction or shrinking it, also in the negative sense. Do you see it? Quite kind of obvious. Okay, now, if I give you a line, so it's clearly an over-parameterization of the line, this one over here, right? Because I have more parameters than those that I need. A line in the space requires just 4 parameters to be described, minimal number. But so how do you come out with these 4 parameters? Well, just consider that a point in the space is 3 parameters, but the line is invariant towards the rotation with respect to the axis of the line, because it's changing. And so you lose 1 parameter, and then it's invariant also with respect to the translation along the same axis. So I lose 2 degrees of freedom, and I have 6. Okay? And I have 4. I had 6, and now I have 4. Agreed? Very good. Now, if I describe a line in this way, I tell you, okay, I have a line, and then I want to apply a transformation to this line. How would you do? Well, the straightforward thing is that you take the point. If you transform a line, you transform every point of the line, right? And you for sure will be transforming the point P0. Okay? Understood? And what would happen to the direction? Well, the direction doesn't have a translation. So if I apply a transformation to the direction, the effect is that I don't apply the transformation, but I just apply the rotation to the direction. Okay? Understood? So if I have a certain transform T, which is consisting of a rotation matrix and a translation vector, or if you want, you can represent it as a homogeneous transformation matrix, I can obtain a line L1, which is obtained from the line L0 by applying the transform T. The line L1 will have parameters P1 for the point and D1 for the direction. This will be a unit vector, where P1 is obtained by the point P0 applying the transformation. and where d1 is obtained by d0 by applying only the rotation. Okay? Obvious. Silly. All right. Then, new problem. Now, let's imagine that we have two lines. I have 0 concurrent viewers, means that all my audience is here. Now, let's imagine that we have two lines in the space. Okay? Two lines in the plane, they always intersect, or they are parallel, which means that they will be intersecting at infinity, if you want to see it this way. But two lines in the space, they do not always intersect. Right? Because you could have lines, I mean, two lines like that will not intersect. Anyway, you could decide, you could ask yourself, okay, they don't intersect, I'm happy with that, but what I'd like to know is, given this configuration of two lines, what is the closest point on one line and on the other? Okay, guys? Now, let's think about what would you do to calculate this closest point. Intuitively, we could have a direct approach, a direct procedure, which would consist on calculating, given two lines, you could calculate the direction which is orthogonal to both. The direction which is orthogonal to both is this. And being orthogonal, it guarantees that between the two lines, that this will be the direction on which the two lines will have the minimum distance. Right? Once you have the orthogonal direction, you could apply the transformation that maps the orthogonal direction to the plane. You could invert the orthogonal direction. You could construct a transformation matrix that maps this orthogonal direction to the z-axis. By applying this transformation to both lines, you could flatten them and see them, let's say this way, on a perspective view that would render them parallel, and then you could measure the distance between the two. This is one line. But we are interested in finding this point. And so how could we do? Well, we do it, let's say, the usual way. No? For a man with a hammer, everything is a nail. And so we could use our least square procedure. How do we intercept a point on these lines? Well, a point on one of these lines is just identified by the scalar s that defines the specific individual point. Okay? Now, if we are interested in finding the closest point with respect to two lines, we will have to find two points, one point on the one line and one point on the other, such that these two, the distance between these two, will be the smallest than the distance between any two other combination of points in the two lines. Okay? So we could define a delta, a vector, that is the difference between a point in one line and a point in the other line. Let's call this vector delta over here. And clearly it's a function of S0 and of S1, because S0 identifies the point on the one line, and S1 identifies the point on the other line. Now, given a pair S0 and S1, we would be straightforwardly able to construct, to calculate this delta vector. Okay? Now, of which delta vector, but this delta vector is also our error. It's also the quantity that we want to minimize in S0 and S1. Is an error vector, because we are interested in finding a minimum. So let me rewrite this delta vector, which is equal to a point in the first line minus the point in the second line, where the first line is L0, characterized by P0, D0. The second line is P1, characterized by P1, D1. This is the difference. I could rearrange the terms. Okay, now there is a mistake in this slide. You spot the mistake, and I will fix the mistake. P0 should be with the underscore. Okay? Okay. P0 minus P1 goes here. And D0 and the vector and the matrix consisting of D0 and D1 and minus D1, I could take these two vectors, arrange them into a matrix, then if I multiply this matrix by a vector consisting of S0, S1, I have S0, D0 minus S1, D1, and so I recover these terms. So this is a matrix. Okay, a 3 by 2 matrix. Okay, these are 3D vectors because we are in the space. All right. Now it's fantastic because what is this? This is a splendid.
Why is it a 3 by 2 matrix?
What?
Why is it a 3 by 2 matrix?
Because how big your colleague is asking why delta D is a 3 by 2 matrix. It's 2 because I have two vectors, right? No? I mean, this equation should be equal to this equation. So let's eliminate the terms. P0 is here. Minus P1 is here. Okay? Then D0 times S0 is equal to S0, which multiplies D0. And I find it here. And minus D1 S1 is equal to S1, which multiplies minus D1.
Okay.
It's a rewriting in matrix form.
Yeah, because it's transposed.
No. No, it's not transposed. D0 leaves... it's long. It's three-dimensional.
Okay, is it a vector?
D0 is a vector, yes. They are two vectors. It's a matrix consisting of one vector, which is D0, and the other vector, which is minus D1. Okay, you see it now, no? This is a product matrix vector. If I multiply this vector by this matrix, I have D0 as 0 here, minus D1 as 1. S0 and S1 is scalars. Clear? Obvious. But also we observe that this is a splendid, fantastic form. Let me call this vector, this 2D vector S, not bold S, right? Then what is this? This is a splendid quadratic form. Splendid affine form. And we know from what we have studied in least squares that if we have an affine form, we can minimize it by Gauss-Newton without doing any iteration, right?
I'm sorry, I still have a doubt about delta D. If D0 S0 is still a vector, because D0 is a vector and S0 is a scalar. So, and D1 S1 is the same. If I subtract a vector to a vector, I should still have a vector.
Yes, you do have a vector at the end. But at delta D is a matrix. These are the columns. There is a space here. There is a space. There is a space between them. It's not attached. Okay, there is a space. Do you want me to mark that there is a space? I will put a space. No, I'll put a space because otherwise, maybe someone who reads this thingies. Now it's fun to put a space. No? You like it? No. Oh, it's atrocious. No? Do you like it this way? Now it's more clear? All right. There's a space in between. Now, this is a splendid affine form. We know that if we have an affine form as an error function, we rejoice because we know that we can solve it like just one go by calculating by using Gauss-Newton. Okay? So we are interested, what are we interested in finding? We are interested in finding the combination of points S0 and S1, which is S, that gives me the smaller possible norm for delta. So I could write this, instead of minimizing the norm of delta, I minimize the square norm of delta, which is the same, like they will have the same minimum, and then I construct my J omega J, so to say, my H matrix and my B vector, and then I calculate the solution by multiplying the inverse of the H matrix by the B vector negating them. Okay? I think it's obvious, right? So automatically we have solved, we're able to find the assistance for which we have the closest point between the two things. Yes, Francesco. Oh, the unique viewer, Francesco, says yes, delta D is not D0 minus D1, but D0 comma D1 or bar D1. Okay? Yes. Clear? Very good. So we are able to find the points. Now, once we have the points, we could, obviously we could find the point which is in the space, which is closer to the 2, because we have the 2 points on the line, and we could just like pick up the midpoint between these two, right? And that will be the point which is exactly equidistant between the 2 lines, and that it has minimum distance between them. Okay? Midpoint, does it trigger something that you might have seen in computer vision? Right? Line intersection. Now, what is a condition that must be verified if I want 2 lines in the space to be intersect? Okay. This condition is, let's write it down in general. We have a line which we call L0, and another line which is called L1 with the usual symbols. Now, in order to verify if 2 of these lines intersect, what could we do? We could pick up 2 random points on these 2 lines. Okay? Any one and then. Being this point random, let's pick up just the point P0 and P1. Because we can pick up any, so we can also pick up P0 and P1. Okay? Now, these 2 points, they form a vector. The difference between these 2 points forms a vector in space. Okay? Now, if I tell you what is the direction on which you should measure the minimal distance between the 2 lines. The direction in which I should measure the minimal distance is the direction which is orthogonal to both. Right? What is a direction which is orthogonal to both lines? The cross product is obtained by the cross product between D0 and D1. Because the cross product between 2 vectors returns a vector which is orthogonal to both. Okay? So I have this direction, which is the cross product, which is the direction basically which is on which the distance between the 2 lines is smaller. Okay? And then I have 2 points on the 2 lines. What should happen in this case is that if I project this vector, which is a vector between 2 points of the 2 lines, onto this axis, which measures the minimal distance, on which the distance of the minimal distance lies, this distance should be 0. Like, so to say it, I will try now to go on the blackboard to visualize it. It's very risky. Yeah, hopefully you see something, and hopefully there are chunks. Yes. We have a line in the space, right? With its point P0, and with its direction P0. This is the direction, right? We have another line in the space, so this, okay, with its point P1, and with its direction D1. All right? Yes, also people from home see. Now, we see them, and it's horrible to see them, like, you know, flattened, right? Let's say that the minimal distance between these 2 lines is here, because of the way we observe, right? Now, if we pick up a vector, which is, as I wrote there, P0 minus P1, say, for instance, this vector over here. This vector over here will be the orthogonal, the orthogonal direction will be the cross product between D0 and D1. So it's any of the vectors which is parallel to this. Okay? Now, if I operate a transformation, I operate a transformation that takes this system of 2 lines, right? Imagine that we are moving this rigid body and orienting it so that this vector over here is parallel to the z-axis to this axis over here on my blackboard. Okay? So I'm now taking these two lines, rotating them, so that I see them from the side. Okay? By seeing them from the side, it means that the two lines should be parallel, right? Okay? Agreed? And how would I see this vector P0 minus P1? Well, I would see something like that. Okay? Or in particular, I would see, if I take P0 to be the origin, I would see something like that. Okay? So this vector over here will become D0 cross D1, or D1 cross D0 if I want to flip it, doesn't matter really. And this vector here will be P0 minus P1. Okay, now, when do they intersect? They intersect when they match. And what is this distance over here? This distance is the dot product between the difference P0 minus P1 and the cross product D0 cross D1. Okay? Clear? And this is the line intersection condition that I've written here. Well, actually, this 0 is not a pole 0, it should be a regular 0, because it's just a number. Do you visualize it this way? Very good. Now I become smaller again. Smallify myself. All right. All fine, all good? Next. Bear in mind, this is the line intersection condition. Okay? Now, imagine that we have the following scenario. We have a fan of lines, un fascio diretto, that are all passing from, so we have two lines, let's say, one line, right?
I have a question about the procedure we used before in order to get the minimum distance between two lines.
Okay.
Why can we use that? Okay, we found a new S found by the admin of the function. We compute again the error.
Which one? Which one? This one over here,
no,
or the one before?
The one before.
The one before. This one. Okay.
Here. Okay.
Yeah.
Of course, if we take the S which minimize the error.
Yeah. But this is I understand. But this how to say, this condition of your colleague says, why don't we use the very same? Another line intersection condition would be that that we find an S for which delta is 0, right? Yeah, this is for sure another intersection condition, but it's more. It requires much more calculations than this intersection condition. Okay? And also this gives us much more than what we really need, because if I'm asking here, I want to know if two lines intersect, you can immediately tell. I'm not asking you the distance. I'm telling you, tell me whether two lines intersect or not. Of course, there will be a relationship, because this will be in general a number, and then if this number, the closer this number is to 0, the more likely is that the lines intersect, yeah. All right. Now, another scenario. We have one camera, one object, which senses the world, which we could picture as a set of lines that are departing from the same center. No? And then we have another camera, which is located in another position, which observes, let's say, the very same points in the environment, which will result once again in a set of lines. Okay, guys? Is that clear? Okay, now, we know that the first camera is located at the origin. If it's located at the origin, let's say that 0 is the point, and then the direction will be a direction. Also, the other camera in its own reference frame, with respect to its origin, the other camera will talk about directions, but it will forget the position, the origin of the lines. Okay? So we are talking about two lines, each one in its own, let's say, reference frame. Okay? And they are both passing for the origin. Now, let's say, now we want to express the position of these two lines, each one with respect to its reference frame, if we assume that we know the position and the orientation, let's say, of the first camera with respect to the second. Okay? Or the second camera with respect to the first. It's the same. Okay? Clear? And so we say that the second camera is located at a certain translation t with respect to the first, and at a certain rotation r, right? Clear? And so we could map, we could obtain a certain line, let's call it L prime with 0, which is characterized from L0, right? Which is characterized by a certain translation vector, which is the translation applied to t, and a certain rotation matrix, which is this rotation matrix. Okay? Is that clear? Because we don't apply the rotation to the why don't I have here R, like if I wanted to apply the transformation to the line L0, I should obtain a point P0, which is R P0 plus plus T, right? But given that P0 is 0, if I multiply 0 by R, I just obtain T. I just obtain 0, that sum by T gives me T. Clear? Very good. So I have the line, right? Now, I have two lines in the same reference frame. If I have two lines in the same reference frame and I know that these lines, they originate, they pass through the same point in the world, this means that these two lines should be intersecting. Okay? So we could write the intersection condition between these two lines. Which lines? Between the line L1, which is 0, D1, and between the line L prime 0, which is characterized by this equation. Okay? And so this intersection condition, if you look back and you replace the things, if you go back to this equation and you replace the terms that are in here, so this is the equation for L prime with 0 and 0 D1 is the equation for the second. Okay? Just do query replace of this expression of these values, this one and this one, into this expression, okay, you will obtain that the intersection condition expresses this cross product equal to 0. Now, bear in mind that sometimes for own convenience I might decide to put a minus in front or to negate the expression. Anyway, 0 has to be 0 even if I invert the sign. Okay? Now, I've written the intersection condition for two lines, assuming that these two lines pass through camera centers and that one camera is rotated and translated by T, R and T with respect to the first. Okay, guys? Now, having written the intersection condition, if you go on Wikipedia and you find a bunch of identities, algebraic properties of the cross product, okay, we could manipulate this intersection condition. So by using this expression over here, A dot B cross C is equal to C dot A cross B. This is one of the properties, algebraic properties of the cross product, how it distributes with respect to the dot product. Okay? Now, if you do a query replace of this expression and you identify the terms and you say T should be equal to A, C should be equal to, so B should be equal to RD, and C should be equal to D1, and then you apply this, we obtain this expression over here. Francesco says, we are intersecting L1 in the reference frame of the first camera and del 0 in the reference frame of the second camera. No, we are Francesco. Francesco, we are intersecting, we are using the very same reference frame, which is the reference frame of L1. Okay? Or actually, like, yeah, I should be the first camera. The first camera is at position first. Better, because we moved the first line, right? Okay? It's not the second. We are applying the transform to the first line, not to the second line. Yes, Francesco. Okay. Because L0 is here, L1 is here, right? Now we apply the transformation to L0 to obtain T and RD, right? We are transforming L0.
Yeah, but L0 and L1 are referring to the first camera.
L0 is referring to the first camera. L1 is referring to the second camera. L prime with 0 is the transformation of L0, no? With respect to the second camera.
Okay, so L1 is
L1, each of those these two lines are in their own reference frame of the cameras.
Of two different cameras.
Of the different cameras. In order, I need to do the intersection on this very same reference frame, right? And therefore, I need to apply that to calculate this transfer.
Okay, that's because you said
yeah.
they are expressed on their own frame.
Yes.
Is two different.
Exactly. Exactly. Okay? Clear? Now, we have done this fantastic cross-product identity. We have applied and we find that D1 multiplied by T cross R D0 has this specific expression, right? And then also, we could replace the cross-product over here with a, I think you're familiar with it, with a cross-product matrix of a vector. Are you familiar with it or not? The cross-product is the skew-symmetric matrix of a vector, right? That's the cross-product matrix that expresses. It's a 3×3 matrix, which is skew-symmetric, symmetric. By replacing this, this cross-product with its own matrix form, and by we obtain this new formula, which is basically the same as before. Now, remember, what is the domain of this expression over here? It's a scalar, right? Because it's a 0. It's a dot product of two vectors, right? So, if we have a dot product of two vectors that is a scalar, we could transpose it as much as we want, right? So we could just like transpose both members in here, and then remember that once you, and we could also negate it, and then in the end we end up with this expression over here. And we could identify that there is a specific relationship that correlates the rotation and the translation of the between the two cameras and the directions of the points that should be projected. Namely, this expression here should be 0. And the value of this expression is a scalar, because it's a 3×3 matrix which is multiplied on the left and on the right by a vector. And this expression here should be 0 in order for the points to intersect. So, if I have two cameras, not that I can put two cameras anywhere I want and the points intersect. No. If I know that the point originates from the world and it's projected on the two cameras, and I sense them with certain direction, there is a specific relationship that these two directions have to obey. Okay? Clear? Very good. Now, if you are interested in finding the epipolar lines, which means I'm interested in finding all directions. I have a camera that observes a point, and I have another camera in another location, right? And I'm interested to see what are the directions in the second camera that that are admissible for this specific transformation and rotation, so that it projects from the same points. So imagine I have a camera with its ray over here. This is my first camera. I have another camera. If I don't know which point on the line projects onto this other camera, I would observe this ray of the first camera as a line on the second camera. Right? Because I see it from a side. And this line is the so-called epipolar line, right? And I could describe it as a set of directions. How would you be able to find all possible directions? Well, it's quite easy because you know that these directions, on the second camera, they have to obey the intersection condition. So you could solve for D1, you will have that, let D0 be the first camera, or D1 be the first camera, doesn't really matter. You could obtain all the D0s by solving this system. It will be a null space of this system.
So our goal is to find our epipolar line in all the possible lines.
We could. It was just like an addition to it. But the important thing is that we found this interesting relationship that must be true if D0 and D1 observe the same point in the space, in the world, assuming that the two cameras are offsetted by R and T. Okay? Clear? Now, and we will call this matrix here, which is a 3 by 3 matrix, otherwise the system would be not dimensionally consistent. We could call it E. It stands for essential matrix. Okay? Now, we observe one thing, that this E matrix contains somehow both R and T. It's a result of both. And our question is like, okay, now, assuming that I give you a matrix E, would you be able to extract from this matrix E the rotation matrix and the translation vector? This is called camera resection. And the answer is yes. Okay, now, how could we do, given E, how could we extract the rotation matrix and the translation vector? Observe one thing, we will not be able to extract the true translation vector because the configuration of the two cameras, right? I could move the two cameras along the directions without rotating them, and therefore I will have a zoomed, I will have a zoomed version of the scene. So I will not be able to estimate T, I will only be able to estimate the direction, to extract the direction of T, because T is not contained into the matrix. Now, it turns out that the rank of this E matrix, which it has a null space of dimension 1, turns out that the E matrix, because of this underdetermination, has a null space of dimension 1. Okay? Now, what happens if we take E and we calculate the SVD decomposition? Well, I already said that E has a null space of dimension 1, at least. And so having a null space of dimension 1, for us, it will mean that the singular values of this E matrix, one of the singular values of this E matrix will be 0, because it has a null space of dimension 1. Okay? So we will have, in general, two, let's say, singular values which will be non-zero, and one singular value which will be 0. Now, by the properties of the SVD decomposition, we know that U is orthonormal and V is orthonormal. Okay, guys? That clear? Now, a little game. Let me, and the matrix of singular values has this formula. Now, let me introduce the convenient matrix W. This is a matrix. What is this? Well, you could observe it and you could see that this matrix W is a rotation matrix, because each vector is has a unit norm, and each column has a unit norm, and the columns are orthogonal to each other. Because if I multiply this by this, I get a 0. If I multiply this by this, I get a 0, and so on. Okay? Very good. Now, and it has that determinant 1. Now, what happens if I multiply this matrix W to the left by the matrix of singular values S? if you do it, if you do this product, you finally obtain that this matrix W, this multiplication has the effect of swapping basically sigma 1 and sigma 2. Okay? So if you do this product, this times this, you obtain on this column, on this riga, colonna, 0, yeah, you obtain this if you do it by hand.
Why the values on sigma 1?
Maybe I made a mistake.
Yeah, maybe they are.
Maybe it's swapped. So sigma 1. Yeah, sigma 1 minus sigma 2. But it would work also the other way around. Sorry, I could fix this. I will fix it. This, I mean, here. It's easy, eh? No, not cooperative. Come on. Okay. It's nice, eh? Now you understand why I make mistakes sometimes. More than sometimes. WS, here. Sigma minus sigma 2 and sigma 1. LaTeX? No? Oh, okay. Yeah, it worked. Okay. Happy with that? Right. Now, if you, yes, this should be consistent. Now, if you would apply this, transformation again by multiplying W transpose that I remark is a rotation matrix. If I multiply once again by this matrix W transpose to the right, I will obtain once again the matrix S. Okay? So I could replace anywhere I want. Instead of S, I could write W as W transpose, because they are the same. Okay, guys? Now, if I embed this business here into I substitute this expression for S into the SVD decomposition that we know it should be equal to E, I would get U, W, S, W transposed, V transposed, just like by expanding S. Okay? Now, remember that if I take a rotation matrix and I multiply this rotation matrix by its transposed, I have the identity. So I could easily manipulate this expression here by inserting after W, V transposed times V, which is the identity. Okay? Now, if you proceed by identification of the resulting expressions, you will find that this first part is obviously a rotation matrix because it's the multiplication of a rotation matrix times W times, which is a rotation matrix, times another rotation matrix. Okay? And what is this? You might observe that this object of this SW transpose or WS SW transpose is a skew-symmetric matrix. And it's a skew-symmetric matrix which is multiplied by a rotation matrix to the left and to the right. And I get once again a skew-symmetric matrix. So basically I was able to decompose my essential matrix in the product of a rotation matrix and a skew-symmetric matrix. Okay? And this skew-symmetric matrix will contain the translation. And then I can proceed by identifying the elements of T. Okay? This is called camera resectioning. How to extract R and T from E. Now, I have to warn you that if you use this process, you will have not one solution, but you have different solutions. How many? 4. Because we will find the translation, we have to try the translation, but also the opposite translation is valid because it would be a reflection. And also like seeing it from the other side, like moving the camera system the other way around. And then we also have W, we have to try the decomposition for W, and also for W transposed. That would be a reflection, so speculative. Okay? Because if we have the two cameras mirrored, then everything looks the same. So we will have 4 possible solutions.
But one of the 4 solutions is the exact translation.
No, it's not the up to a scale. It's the direction. Okay? Is that clear?
Just to make it clear, which is the difference between maybe the ability, the solution of T minus T and W transpose?
The point is that you have directions and you don't know which directions are which, right?
Yes,
because
simply, I understood that in the translation part, the ability is given by the reflection. Right? But you said also that in W, the ability is given by the reflection.
it's given by, I think, a rotation of both reference systems, I think. Reflection is swapping axes.
Yes, that's great.
Okay, T is, no, W and W transpose is the reflection, and T and minus T, I think, is the ambiguity of the direction. Okay, but you have 4 solutions. The thing is that it's just an algebraic procedure. So in the end, you end up that you have 4. The same demonstration would work out with T and minus T and with W and minus W. That's it. You have 4 possible solutions that will satisfy this E. Okay? And normally you don't know which one. And so what do you do to find it out? Let's see. Okay? Now we would be able, given a matrix E, to if someone would give us this matrix E, we would be able to extract the relative rotation and translation up to a scale between the two cameras. But still, we need to have someone that gives us this matrix E, right? And the question is, how do we estimate this matrix E? What do we have? Let's say that we have the oracle that tells us for each point what is the direction on which it projects in the 2 images. Okay? This is our input. Of course, we can't have one single point. We need to have several points in order to resolve this problem. Okay? Let's say that we have them. The minimum number with this solution is 8 points, with the solution that I'm proposing you. Let's see how could we estimate this matrix E from a certain number, many, no, corresponding directions without knowing the camera translation. Right?
Okay, sorry, maybe I lost the focus for a while. We have chosen this methodology starting from 2 cameras, 2 lines. Then we have built the E matrix, and from the E matrix we have shown that it is by the SBT decomposition, etc.
We can extract R and T from the E matrix.
R and T we can extract. But now why we need an E matrix if we have if we started from this condition?
No. Your colleague says, why do we need an E matrix if we started from this condition?
Yeah.
This is another problem. Now we have seen that from E, I would be able to extract R and T. Take this aspect and put it on an abstract. Now, that's another problem. I give you a set of directions on the 2 cameras that I know it by pairs, that this direction in one camera corresponds to this direction in the other camera, and so on. And I'd like you to estimate E from the directions without knowing R and T. Okay? Is that clear, the problem? Now, how could we do? Well, the very first thing that we do is that we rework our, let's call it epipolar constraint, which is 1 point transpose, which multiplies a certain matrix E, which multiplies T. Okay? Now, once again, we could rewrite this expression over here in a matrix form, where we would have, if you write it down, now this is A11, A12, no, the coefficients. If you write down on paper the product x prime 1, x prime 2, x prime 3 transposed, multiplied, E11, E12, E13. So if you write down, if you unfold this expression and you rearrange the terms, you will figure out that this constraint, which is the line intersection constraint, could be rewritten in this form. Okay, guys? Is that clear? So this is a multiplication by a vector, horizontal vector, times a 3 by 3 matrix times a vertical vector. If you do the and this is scalar. If you do the products, you will have the sum of 9 products, and then you group the terms, then you will find out that you could express this vector, this product over here, by a certain horizontal vector A, that I just wrote as bold A to denote it's some sort of a matrix, which multiplies a certain vector E that contains the coefficients of the matrix E. Okay, guys? Is that clear? Now, having this, we could use, what is this? This basically expresses how much a constraint is violated. It should be 0, and then if I have many points denoted with I could decide to find the essential matrix E, which minimizes the square of the epipolar constraints. Okay? Clear? Because this is equal to AE. I have many points, so, and this is the square of this object over here. I have many points, I could just calculate this expression and minimize it. Now, it turns out that it's obvious that the obvious minimum of this expression is 0. Because if I set E to 0, I find 0, I'm happy with everything, right? It's definitely not what and this is a result of the fact that the essential matrix has a null space. It's underdefined. So, what could we do in order to find an essential matrix that has some sense? We could impose a constraint. Which constraint? Because remember another thing, that this expression over here, D transpose ED, is valid if it's equal to 0. It's valid for any E up to a scale, right? Because if this expression here would be equal to 0, if I multiply it by 2, I get once again 0. If I multiply it by 3, I get once again 0. Do you understand? So I need to delete, to impose a constraint that makes my essential matrix non-null. So I want to have, of all these solutions, I don't want to have the 0 solution. Okay? How could I do? I could simply enforce that the norm of the coefficients of my matrix E is equal to 1. So of all these possible scalings of the E matrix, I just want to have the E matrix was squared sum of the values is equal to 1. Okay? Cool. So I could write down this minimization as a constraint minimization, where I'm interested in minimizing the square norm of the point error, let's call it this way, subject to the condition that my the essential matrix is coefficients sum up to 1. The square of the essential matrix coefficients sum up to 1. Okay, guys? Is that clear? Now, it's obvious that I think I do not have to explain how I went from this expression to this expression, because I just put the for loop where it requires to be. Okay, now, how do we solve this problem over here? So we want to find the essential matrix that minimizes this expression, which I could rewrite simply as E transpose HE, where H is a 9 by 9 matrix, because it's the product of a vector which is 9 by 1, no, 1 by 9 by a vector which is 9 by 1, right? Clear? The sum, actually, of many of those. Now, I'm interested in minimizing this expression over here, subject to the constraint that E transpose E is equal to 1. So how do you do? If you look in analysis 2, I think, you have studied the Lagrange multipliers. Do you remember them? Something? Okay, Lagrange multipliers is a way of carrying on constraint minimization. In order to minimize a certain function, this is the function. This is the function I want to minimize, and this is the constraint, or this is the constraint that I want to be respected. Okay? So, to do this, what you do is that you calculate the so-called Lagrangian, which is this expression over here, which is defined as the function to be minimized minus lambda times the constraint, where the constraint should be an expression for the constraint equal to 0. Okay? So if we want to have E transposed E equals to 1, we have to write the constraint in the form E transposed E minus 1 equals to 0. Okay, guys? So you construct the Lagrange. Then you find the minimum by differentiating, by solving the following system of equations. Okay? You construct out of this Lagrangian a system of equations. The first equation of the system is obtained by differentiating the Lagrangian with respect to the variable you want to minimize, which is in this case E. Okay? So this is the first equation of the system. If I differentiate this equation with respect to E, I get straightforwardly 2HE minus 2 lambda E. Okay? And the second expression of the system of equations that you need to solve is the derivative of the Lagrangian with respect to lambda, which is the constraint, basically. Okay? So we want to solve, basically this is the derivative of the function subject to the constraint, and this is the constraint itself. Okay? So this is a system of equations that we want to solve. Let's look really well at this system of equations. Okay? We have 2hv minus 2 lambda v. Does it recall you something? Of course, I could delete the 2. If I write av minus lambda v, does it ring a bell to you? av minus equals to lambda v. Does it ring a bell? It's an eigenvector. It's an eigenvector problem. So the good thing is that we have that this problem can be solved, and so we know that E should be an eigenvector of the matrix H. Okay? That's the very first thing that we know. And we are happy because we have programs, we have procedures that are able to calculate the eigenvectors of a matrix. Okay? So in order to find the essential matrix, we could just like extract all eigenvectors of my of my H matrix. And then we rearrange them in theory, and then we obtain the essential matrices. But then we have, how many eigenvectors will we have for H? We will have 9 eigenvectors, right? And the question is like, which one do I choose? And then the answer is then simply look at the cost. How much is the cost? The cost will be E transposed HE. Okay, if E is an eigenvector, the cost will be I'm interested in minimizing this. So I have an eigenvector, I just evaluate this expression, right? But if you remember that HE is equal to lambda E, we could rewrite the cost as E transposed lambda EJ. But given that E is an eigenvector, it has square not equals to 1, right? So it turns out that the cost of this solution for a specific eigenvector is equal to its eigenvalue lambda. So the game, in the end, of determining the E matrix would simply consist in calculating the eigenvectors of the matrix H and picking up for as E the eigenvector having the smallest eigenvalue, because the eigenvalue will be the cost. That clear? Okay. So now, let's see where we are. We started talking about lines. After talking about lines, we expressed the line intersection condition. From the line intersection condition, we derive the essential constraints, this E matrix, these constraints that should be respected. And then we stopped for a second and we say, hey, but there's no one that tells me where the two cameras are. Let me figure out where they are, right, from the projections. That's something that I can have from the data. So, how do you do? Well, let's start extracting, let's start from, another thing that we have found is how to extract the rotation and the translation of the two cameras from the matrix E. Then we said, but there's no one that tells me R and T, so I can't have access to E. But I said, okay, you could have access to E if you would know which projection is which. By using this process, you would obtain an estimate of E. Okay? Clear? Once you have this estimate of E, you could do something with it. For instance, extracting R and T. Okay? But once again, we know that that's basically the game of the game of the 8-point algorithm. It's called 8-point algorithm, this program over here, because it requires at minimum 8 points to function, to find the solution. Okay? Clear? Once I have the E matrix, I could straightforwardly apply camera resection, so extract R and T, and so I have 4 possible candidates of rotation and translation from one single set of correspondences. Okay? In fact, what we have done now is to take the easy way. Because in fact, the E matrix, if you really look at it, the E matrix has only 5 degrees of freedom. Why? Because the E matrix is the result of a rotation matrix, which has 3 degrees, the product of a rotation matrix, which has 3 degrees of freedom, and a translation vector up to a scale, which has 3 minus 1, 2 degrees of freedom, right? So if the E matrix has only 5 degrees of freedom, in theory I should only need 5 points, let's say this way, to estimate this E matrix. The point is that the 5-point algorithm is really, really complicated. It's a really complicated derivation and really complicated to write down, and it requires in the end to solve a 12-degree, I think 10-degree equation polynomial. I mean, it's kind of complicated. I never really understood it, I have to say. There are simpler solutions that require less points, 7, 6, 5, 7, 6. We, for now, and in this course, it is not a computer vision course, we are happy with the 8-point algorithm. So we are happy of requiring 8 correspondences to find the E matrix. Okay? In fact, what we are estimating is something a little bit broader than E. We are estimating something which is called a fundamental matrix that incorporates also the camera matrix K in this process. So we have an E which has a little bit more degrees of freedom, unless we do one strange trick. If we constrain the direction to be the unit norm. In this case, we will be operating on the essential matrix. Okay? Anyway, the question is, let's say that I now have obtained with the 8-point algorithm. The question is, how do I get the translation? And there are many, many ways, and then I will tell you the robotics way, which is going with the X. If you follow a computer vision book, they talk about seriality constraint and figuring out what is in front from the algebraic solution. My solution is simply, I have a rotation matrix, a translation matrix. I have a set of directions. What I could do is simply to triangulate the points, because I have the directions. I know how to triangulate the points because I told you before, find the intersection, right? If I find the intersection, I automatically find the point in between, right? And I triangulate for each solution, for each R and T, I take all the points that I have, I triangulate them all, and the solution which is good is the one on which all points fall in front of the first camera first, on the field of view of both cameras. How do you know that a point falls in front of the camera? Well, it has a positive S, because we oriented the S in our line in a way that it exits the camera, right? So if I just count how many of these triangulated points fall in front, the one that has more points falling in front is the good one. Okay? Clear? Very good. And, okay, now, I mean, this, now I will show you also some program, some piece of software that you have actually. And then this basically concludes a rather small recap on projective geometry. I mean, remember the disclaimer. So it's not that after this lesson you can say, oh, no, I know computer vision. But at least you have an idea on what it means in essential matrix. You have an idea why the 8-point algorithm works this way, and you have an idea on how to triangulate points. Okay? This is a disclaimer. I want to have feedback. Was it clear, everything?
Could you provide us an example, a spoken example in which we are asked to, we are asked to compute E, then R and T?
No, I provide you the code. I don't provide you an example. I provide you the entire code that implements all these algorithms, because these pieces of software are on the slides.
I got this algorithm is clear, all the passages, mathematical passages, but behind these passages, why we should apply this algorithm? I have not understood the practical example in which we are asked to do this.
Oh, okay. A colleague of yours.
The location inside the.
Okay. You're saying, where do I want to apply this problem? For instance, we will see it in a while. If you want to bootstrap, or if you want to reconstruct a 3D scene only from camera images. Okay? Then what the normal engines of computer vision do, like, I don't know, that's photosynth or so on and so forth, how do they work? They work this way. They take all the images that you have. From every image, they extract features. And they, for a moment, forget the images, right? And then they compare each pair of images, A with B, and for each pair of images, they try to figure out which features in one image correspond to which feature in one image. And therefore, they have these vectors, not these direction vectors, right? And then once they do that, they're not happy, because what they do, and we will discover it in the next lesson, they apply a certain validation procedure that is called transit. But in order to apply, they have to figure out, for each pair of camera, how they are positioned in the space, with respect to each other, right? Or in general, they estimate the putative rotation R and T, okay? They have a way. They will do it by implementing something a little bit more complicated, but that uses the 5-point, 8-point, whatever. And so you have a set of cameras up to a scale, right? Pairs. And you have many of them. No? And you could form then what they do, but now I will make it simple to you, because they do something slightly different. But what you could do at this point is to try to resolve. You remember that we resolved the problem of similarities? Okay. What you could try to do is to formulate a problem of similarities. So when you are interested in finding the relative rotation and translation of all the cameras, that you have one camera with the next, but two cameras also observe each other, no? Let's say you have this mesh of relative position of cameras, and they trying to find out the position of the cameras that minimizes that is mostly consistent with each other. Okay? This is not really what they do, but just to give you an idea. You have these relative pairwise constraints, and they do this. In fact, what they do is to proceed, given each pair of cameras, they could formulate, so you have constraints, you have n variables. Each variable is a transformation of a camera. Okay? They proceed by estimating the relative rotations between all cameras. Okay? And this is a closed problem, because, no, not closed, but this is a problem that is fully defined in a sense, because you don't have scale ambiguities, rotations. Okay? Once they have determined the rotations between the cameras, they block no, first they estimate the relative rotations between pairs. And then they want to find a global that satisfies each pairwise constraint. They find the global rotations of everything. Once they have found the global rotations, then they start zooming and unzooming. Basically, they try to determine a scale for every pair of cameras that satisfies the entire system. So they resolve the translation problem. This is the third stage. Then sometimes they have to use a line search, because it's not really easy. And then once they have resolved the translation problem, they do bundle adjustment that we will see in a couple of lessons, where basically they adjust all possible position of the camera and all possible position of the triangulated points in the world in order to minimize the reprojection error of each. At the end, you have a constellation of cameras and of points that is mostly consistent with the photos that you have taken, up to a scale.
Okay, once this step is done, what?
You sell the model, typically.
Sorry?
You sell the model, because normally this is a software that you do for the people that want to do 3D.
I mean, we are able to reconstruct for example, the path that a robot has done given the image.
Yes, so you are able to construct a scene. If you don't have fun in reconstructing a scene, then but that's already a cool thing by itself, right?
Okay, perfect.
No?
Got it. Thank you.
All right. Now let's see some little program that will be one-to-one with the algorithms that we have seen. Sorry, wrong window. Save. And then I will commit it. Then there are small typos, I will fix them later. Pro. No. Octave. You have an entire thing. And basically, you have, like here I implemented you a simplistic, all these routines that we have seen implemented for fun, okay? What I've implemented is quite interesting. I've implemented the, not the pinhole projection, right? Because the pinhole projection you see everywhere. I've implemented something slightly different. Yes, no. I implemented here the pinhole projection. So basically, first function, project a point in the world onto the image plane, right? So you take a point, you multiply the point by the camera matrix, you perform the homogeneous division, and given that we assume that we don't have where is R? There is something, I think, where is C and where is R? And why does it work? 1 second. Octave, click. Okay. So, test the people. Yeah. Okay. Didn't complain. 1 second. First, I have to test the people and dot. Okay. I don't know where I've put R and C, to be honest. But simply, you know why it works? Because I never call this function. Okay. First function, I give you a set of points in the world, I give you a camera matrix, and I ask you to calculate me the projection of the points. The projection of the points will be clearly 2D. In order to project a single point, you have to take the point and multiply the point by the camera matrix, and then you have to perform an homogeneous division. That's it. Okay? And this is what basically is done here. What this function returns is a vector. This is a matrix. This is a matrix of points, 3 by n. And what it does, it returns a matrix of points which I assume to be 2 by n, which is each point each of these word points mapped into the image point. And it also returns a vector of Boolean that tells you whether these points are inside or outside the viewing frustum. Okay? Where R and C, I assume, okay, yes, now I remember, R and C are extracted from the camera matrix, okay? Because the camera matrix has a fx, fy, which is the optical, the principal point, and so I just take the principal, I take the principal point and I multiply it by 2, because it's in the middle of the image. And then I determine somehow the width and the height of the camera. Okay? That's the game. Okay. This is first point. There is another fantastic function which is called triangulate points. You remember, guys? Triangulation, find the minimum point. Triangulate point works that I have triangulate a point passing two true lines. One of the lines is passing through the origin and the other line and has a direction vector d1, and the other line passes to a point p2 and has direction vector d2. So this allows me to try, one will be my camera and the other one will be the line over there. And what I will have is a Boolean that tells me success, and I will have a point P in the space, and I will have also E, which is the error, which is the distance between because the 2 points might also not intersect, right? I might have a little noise in between, and so the 2 lines will not fall exactly in the same point, right? And what I do, if you look carefully, is exactly what I've done in the slides. So I calculate this linear system, and I resolve it, I find S, and so on and so forth, right? So I'm able to triangulate a point, I'm also able to triangulate a set of points, not one, n, okay? So in order to triangulate a set of points, I assume that I have one image, P1, one set of directions, which is the points on the one image. Another set of points, which is the points on the other image. I assume that I have a transformation that I call X, which is the transformation of one camera with respect to the other one. And I assume that the two cameras are characterized by the same camera matrix K. Okay? And in the end, what will I return? I will return the number of points for which I have a successful triangulation. Means that I might have points for which S1 and S2 are, for instance, negative, which means that they are behind the cameras, right? Because I might have I don't know, this has to be robust, shouldn't be work only on ideal conditions. I might also misplace cameras. So I might carry on the triangulation, and the triangulation might return me a point which is behind both cameras. Okay, guys? Clear? So
in this case, we don't know the signal of the scale value. We have to discover it.
X is a transform, right?
Okay.
Okay. X is a transform that expresses the pose of the word with respect to the second camera, no? So the pose of the first camera with respect to the second. Okay? In this case, we say, I give you a bunch of directions, and I'd like you to triangulate, I give you a camera position, another camera position, and I want you to calculate the points in the space, given these two bunch of directions which are corresponding, right?
But in this case, we don't know if the pointer is in front or...
We don't know anything. We just know the direction. Okay. We know the direction, and we also know that, given the optics of the sensor, that the point should be in front. But if the transform is wrong, I might find that the triangulation leads me a negative thing.
So from this function, anyway, we expect that it's in front, but...
if it's not, it tells me it's not. Yeah, exactly. So what we will have here, fantastically, I mean, it's just a design. I mean, I think it's it's relatively simple because it's very atomic in terms of.
Just a curiosity, could we estimate if the regularization of the points are in front of the camera, behind, just looking at the error, if the error is higher than between the error of the camera?
No, because you might have two lines that, imagine that you have two cameras that are looking over there, right?
Okay.
One camera which is looking there, one camera which is looking there. The point perfectly triangulates, but in the back of the camera. Then you have an error which is 0. But S1, S0 and S1 will be negative.
Okay.
Your colleague asked, could we just look at the error? The answer is no. You have to look also at the direction. All right. I mean, what this function does is nothing else than calculate triangulate each individual point, right? And what it's going to do is to return the number of points which are successful in front of the camera, the points P, and also a vector of errors for each individual point. Clear? Easy. Now, then we have clearly functions which are straightforward, which is transform to essential and essential to transform. Transform to essential, we have seen it. If we have R and T, we can calculate the essential, where X is an homogeneous matrix. Okay? If you have essential to transform, well, we have the procedure in the book. Now, where we have our W matrix, we calculate the SVD decomposition, and then we try for T minus T, R minus R. Okay? And it will, in the end, what I will do is that I will return only two transforms, because I have one transform for W, one transform for minus W, and then you can obtain T and minus T just by flipping. Okay? All right. That's it. 1 to 1. So second solution for the rotation that you have to try instead of W, W transpose. Is that clear? Okay, there are the fundamental matrix is obtained from the essential matrix by applying this expression, and also vice versa. Just ignore it for a second. And then we have a function which calculates the estimate, implements the 8-point algorithm, which is estimate the fundamental. In your case, it will be the essential, simple, and that's what it does. Now it takes the point, it calculates the vector A, it calculates the matrix H by summing them up, calculates the eigenvectors, and picks up the first eigenvalue. So calculates the eigenvector and eigenvalues and picks up the first eigenvector. Okay? Then the estimate fundamental. Well, let's say that I'm forced here to use K for historical reason, but here you have the cool part, which is estimate transform, the one that we want to have. We have a set of points in the one image, we have a set of points in the second image, and we have a camera matrix K, and what we want to do is to calculate the transform between the two, assuming that we have, in this case, no noise. And what we're going to do is that we have to estimate the essential matrix, estimate the fundamental matrix, and from it extract the essential, which is basically equivalent in our case. We have this E matrix, and estimate fundamental uses exactly the estimate fundamental simple uses exactly the 8-point algorithm. And what we have is that at the end, we have this E matrix, and we have to extract the rotation and the translation. We estimate the rotation and the translation, and then we try for 4 times the 4 solutions, and we try to triangulate all the points. And at a certain point, we will find a point that one of the 4 solutions will have the most points in front of the camera. Okay? Clear? And that's basically it. Now, if you want to test it, there is a program which is called test epipolar that, yeah, test triangulate points, test fundamentals, test. I invite you to have a look at it because, yeah, well, it's not much to be done. Let's do it. No, I had octave here. Yeah. Okay, let's generate a certain generate transform. We generate a transformation matrix. We need it. Let's create a certain number of point pairs, which is points in the same points, but in two different reference frames, because one will be the reference frame of the first camera, the other one will be the reference frame of the second camera, because we need to apply the projection. Just n points, 100 points, 1000. Just not to be able to read or to write, we generate these points. P1, these are the points, right? Generated by me. Then out of this point, we have two set of points. We have the transform, and what we would like to do is to project the points and then to triangulate them again, right? Because we have the points, now we can calculate directions, we have the transform, and now it's the time to figure out whether our functions for triangulate the points work. Clear? Yes? No, I don't. No. What was it? Buffers. Okay. K. I have to invent a camera matrix. Sucks. Camera matrix will be K is equal to 100, 0, 100, 0, 100, 0, 0, 0, 1. Oh. Doesn't like the comma. I'm familiar with octave, eh? No?
Maybe square brackets.
Yes. Better. Okay, yeah. No? Okay. I have this fantastic thing, and what can I do? I have these points, P1 and P2. P1 I have it, P2 I have it. Yes, and I can triangulate them. No, I have to first project them. P, EMG, P1, and is outside. Oh, better. Project point KP1. Okay, we have the points. And then we do it the same for the second one. P2. Okay. And then at this point, no. Is 1 and is outside 2. Okay. And then we can triangulate them. We have P1 EMG, P2 EMG. And that's also another fantastic thing. Prune projected, well, guys, you have a bunch of utilities here. I mean, you can play with one, but, oh yeah, I have to do prune projected point pairs. What does it do? It takes the point P1, it takes the point P2, and it considers only the points P1 and P2 which are present and in front of both cameras, because we generated a bunch of points in the world. If I record correctly. So let's do it again. P1 EMG. Oh, jeez. No. Where was it? F11. Yes?
So basically, then we call doing project point base for every solution, and
Yes.
every solution which has the most points in front of the camera.
Yes, yes. Is outside 1. Was I consistent? Yes. I think that was it. Yes. Okay. Then we have the points P1 EMG and P2 EMG. Now we can try to triangulate and hope that we will have. Remember, we had 1,000. Now we have only 100 because many of them were behind the camera and so on. Now we can try to triangulate. Let's triangulate, triangulate, triangulate pointers here. X I've already calculated. Yes. Okay. That's the triangulation. Yes. And let's see the errors. What was it? Errors. Oh, errors. Errors are small, right? So because we didn't inject any noise. So the triangulation was perfect. You know, we could keep on and try. Now, out of this pair of directions, let's see our x. This is x, right? Now, we know that we have these directions. Now, P1 and P1 EMG and P2 EMG are the points or the directions in the one camera and the other camera, right? We know that everything is perfect, and we know that the points could be triangulated. At this point, we could ask ourselves, oh, let's extract the transformation matrix. Okay, guys? And let's do it. Estimate transform. We'll call it xest. Just to show that this business works somehow. Okay, this is my x, and this is the estimated x. Now observe that the rotation is perfect, but the translation isn't. But what could I do? I could compare the two translation vectors and see, divide one by the other, pointwise, and to see if they arrive to the same constant. Okay? So what I'm going to do now is to calculate the t, which is equal to x, 1, 3, 4. This is not. Yes. 1, 3, 4. And why did it pick me up the last? Because 1, 3, 4. Perfect. And test is equal to xest, right? So I can do t dot divided test. They are proportional. So, and by doing step by step, now I invite you to have a look at the code because there's not much. Now it will be boring, really, if I start here I delete this, here I multiply this. I mean, you can have a look at it by yourself.
The first transform was just to check the solution.
Yes.
You didn't use it all.
No. I didn't use it at all. I just started from the projected points.
Okay.
And then from the projected points, I wanted to figure out whether I am able to extract something that makes sense. Okay? If there are questions, I'm taking questions. I think we have enough meat for today, right? Or, I mean, if you want to do it, I invite you to invest this time in processing these things. Or if you want, I could just go on with the next topic. You choose, guys.
I still have a little doubt. Okay, we said that the TS and T are proportional, but maybe I understood better. You said at the final part of the lesson, you said that we could, by the triangularization, also have an estimate of T, or maybe I'm wrong.
When what I did in this program, like in this program, we're talking about the demonstration part, right? In this program, what I did, I generated a bunch of points in the world. Okay, I transformed these points as if they were seen by another camera, obviously. No? Then I projected the points on the two cameras. Then, given that the scene has to be consistent, another thing that I did is to eliminate from these projections those that are outside of the image. Then, in order to carry on a meaningful triangulation, given that the point to be triangulated should be appearing in both images, I retriangulated the points and I eliminated the points that do not appear neither in one image nor in the other. Okay? And I consider only those that are surviving, so or that are visible from both. Then at this point I forgot about the points in the world, and what I wanted to do is to construct a test for my estimation problem. So I consider only the dimensions which are the directions that were surviving from both, and I run the procedure to calculate the essential matrix. From the essential matrix, I extracted the 4 solutions. This is done in estimate transform, and I tried each of the 4 by triangulating the points. And then I picked up of the 4 solutions the one that has the most point in front, and I said this is my transform.
But there is no way to extract also T from...
I extracted T up to a translation. You can't extract T. It's impossible with the data that you have. With only one camera, you can't. It's not in the data. So, shall I go for the next topic or not? Hello, hello. Actually, it's 14 slides. Okay, will you keep up? I mean, a perfect complement to this lesson is Ransack. Okay, now let's focus on a simplistic problem. A simplistic problem is I have a set of 3D points, and I want to register this set of 3D points, but the problem is that I do not know either the correspondences, or I know the correspondences with very low probability, and I do not insist. Fine, use your data association machinery, but my data association machinery assumes that I have a guess of where I am. So I can't do that. And I can't even use robust kernels because I don't know where to start. So one way, so our situation is even worse. We don't know the correspondences and we do not even know the initial guess. Okay? Or we know the correspondences very poorly, but we don't know the initial guess. So our goal is to find a transfer that minimizes the distance between corresponding points. Okay? This is an example of Ransack. Now, the general schema is the following. As always in robotics, we reason in terms of in probabilistic robotics, we reason in terms of wishful thinking. So instead of looking at the data and say, yeah, how could I get the solution? We think about saying, hey, if I would have the solution, what would be the data? Okay? That's what we do when we construct a prediction model or whatever, when we do a measurement function and so on. We assume that the state is known and we predict the measurements. And then the inference machinery does the rest for us. Now, what could we do in this case? We could bring us in the easiest case that would resolve us the problem. I said we don't know the correspondences, but we, let's say, what could we do if we know not all the correspondences between the points, but we know a minimal set? We know that 10 correspondences in this point cloud are good. Okay? Well, what we could do is to take this initial set of correspondences, these 3 points or 4 points. 3 points are sufficient to register 2-point cloud because they resolve the 6 degrees of freedom. We could take this minimal set of correspondences, 3, put these correspondences, calculate a solution, and we could do this. We could register the points, and after we have put the solution, calculated the solution, we could proceed, let's say, with our data association or with some heuristic to complete the rest. Or, in case we have very noisy correspondences, we could consider, after this solution, how many of the correspondences that we have are good with respect to the initial solution that we have found. Okay? Some sort of voting scheme. So the idea is the following. We pick up 3 correspondences in this case. If the problem is more complicated, we might need 4, we might need 7, 8, right? But we pick up a minimal number of correspondences that are good for us to find a solution. Okay? Is that clear? So in 2D, how many correspondences would I need in order to register in 2D? 2 correspondences, fine. In images, how many correspondences would I need? I said 8-point algorithm, and minimum 8 for finding the relative thingy, right? Because 8 points. Okay. Then once we have this, let's say, minimal set of correspondences, we could find an initial guess. Having an initial guess, we could register the points, and then we could determine how many of the other correspondences, of the other points, are supporting this solution by basically measuring the error of each. Okay, so the game is the following. I start from a bunch of points, a bunch of correspondences. I calculate the solution, so this is the configuration. Say I have these 3. I calculate the solution, which is this one over here. And then I will notice by this solution that there is one point which is not confirmed, and all others are, right? So this solution will have a certain number of good, points, which is good correspondences, which we call inliers. Okay? So, and then if we would have this, once we have done that and we have pruned the bad correspondences, we could calculate an optimal solution because we have now eliminated the evil ones, because we have found an ideal thing, and we could refine the solution by applying, I don't know, a least square optimization, whatever we know that refines the things very finely. Okay? This is the concept. In order to implement this scheme, what do we need? We basically need to have a set of roughly known correspondences between the set. This is in the data. And we also need to have a procedure that, given a minimal, small set of correspondences, is able to retrieve us a solution for our problem. Third, we need another element, which is a strategy that tells us, after we have to compute the solution, whether another point pair or correspondence is good or bad, given this solution. Okay? So we need these 3 components. Clear? Now, here comes the concept of ransack, which is, if you don't know it, try it multiple times and pick up the best. So the idea is that with ransack, you repeat this process for n times. How much is n? We will see it in 2 slides. But you repeat this process in this line. It's random. Your input is a set of correspondences, of which many of them are wrong. What do? You pick up a minimal set. Between this set of correspondence, you pick up a minimal set of good ones, of them, not of good ones, because you don't know which one are the good ones. Out of this minimal set, you calculate an initial alignment. Okay, guys? And you need to have a minimal solver for that. Out of the initial alignment, you can calculate the consensus, which means basically you calculate the error, so to say, of each of the other correspondences, not those that you use to calculate the solution, because they will be automatically satisfied. You calculate how many of them are good, no? How many are supporting your decision, your current set. And then you take this solution and you put it on a side, writing down also how many liars, how many good ones you have out of total, and what is the value of the solution. And then you try it a second time, no? And then you repeat it, and you repeat it. And each time you keep up, if the new solution is better than the previous solution, you check out the previous solution and you keep the best one. You repeat this procedure n times, and at the end you stop. Now we will see how much is n. Your question.
How can we compute an alignment if we are considering more than a pair of points?
You need to, is not, this is a concept. You compute an alignment based on the problem. If you have a 2D, no? A 2D problem, 2D scan, point-based problem, then you can write down a formula to calculate the alignment.
But the alignment is the same between all pairs of points?
You can calculate that the alignment must be the same, because these points, they should confront the same solution. The alignment should be the same. Your colleague is asking, is the alignment the same? Yeah, it has to be the same. These points have to be extracted from the same scene. Right? They should be, otherwise it doesn't really work. There should be one unique solution for which you need a minimal number of correspondences to be calculated. Clear? Now, then how many depends also on the problem, because you might have a 2D problem, a 3D problem, you might have a projective problem for which you need 8 points instead of 3, you know. It's a problem demand. What I'm explaining here is a concept. Ransack is not an algorithm. It's a schema, no? A way of doing things. Like a lot of things that we do, it's not that I show you the algorithm, but it's not the algorithm. Everything is plastic. You can modify it. You can add things. You can reshuffle it. You can do, embed a little bit of these squares inside a piece of Ransack. One can do stuff. Anyway, the schema says the following. Now, having said that, let's remind it, because sometimes there are exercises on that at the exam. The Ransack is a schema. Remember what we need. We need a procedure for implementing it. We need a procedure for seeking for the correspondences. Sometimes we compare descriptors. We do something. Of course, the better are the correspondences, the less trials intuitively I need to do. Because if I have perfect correspondences and I want to implement Ransack, well, just at the first go, I have a perfect solution. And so I will have to test, to try it over and over less times. Okay, guys? Then another thing that we need is a procedure that tells us, given these correspondences, putative correspondences between the two sets, tells us maybe which one gives us already correspondences that make sense. I make you an example. Let's say that I have 2 point clouds and I have a bunch of correspondences. Already when I extract the correspondences, I could pick up sets which make sense. How? Well, I just reason in terms of invariance. I need 3 correspondences to align 2 point sets, right? What is a quantity that is not changed by rotation and translation is the distance between points, right? So I could pick up a triplet of points in the first set and a triplet of points in the second set that have between each other the same distances. Or the distance between P1 and P2 is equal to the distance is a certain value, the distance between P2 and P3 is a certain value, and the distance between P3 and P4, P0, P1, P1, P2, and P0, P2. So there are three distances, it's a triangle, right? On the other point cloud, I better pick up a triangle that has the same size. Otherwise, I will already not have a good solution. Do you agree? So there are embedded invariants that I can use when sampling the correspondences. And then I could calculate a procedure to, or for instance, in case of images, if you know that your camera never flips the other direction, then you try to pick up the correspondences so that if you have a correspondence between one point and another point, on a, let's say, if the order on the image of the correspondences is preserved, because if the camera's never flipped, you expect that if I match a feature on the high part of the image with another feature on the high part of the image on the other camera, then the second feature, which will be lower, will be also mapped with the other feature on the other camera, which is lower. No? You try to use some sort of correspondence to simplify your existence. But in the worst of the cases, you know nothing. Third thing that I need is a procedure to calculate a solution which is immune to poor initial guesses. For instance, ransack, the 8 point, we have seen it. We didn't do any assumption, like for calculating the E matrix. We didn't need to know at all R and T, did we? No, we only needed the directions. The same thing, if we would have to implement this schema on ICP, it would make sense to use the linear relaxation, because the linear relaxation is immune to initial guess. And then the third thing that we need is a procedure to count the inliers, which is basically how much, given that I have found the solution, is this correspondence good, or is this other correspondence good, or is this other correspondence bad? That could trivially be the error in terms of least squares. Okay? Now, in case of ICP, in case of the problem that we have, we don't have much to leverage because we don't consider the appearance. If we would add, we don't consider anything but the existence of a point. So knowing the correspondences in ICP might be like really tricky. It's basically your correspondence set is all with all, okay? All point might correspond with all other points. It's a huge set. So if I have n points, I will have n times n correspondences in the two sets, okay? And this leads to an inlier ratio, which is how many good out of the total number of correspondence do I have, which is pretty bad. It's 1 over n, no? Which is really bad. If I have 1,000 points, it means that I have 1 over 1,000 is a good one of these correspondences, okay? Normally, we define how many good correspondences with respect to the complete set we have as inlier ratio. No? How many good with respect to the total. But in our case, let's say that our two steps is 1 and 2, like procedure to see correspondence, and like we just like our strategy is all with all. Okay, guys? Clear? Then to determine the solution in our simplistic 3D case, what we could do is to use linear relaxation. Do you agree? Yes? Linear relaxation, you believe me that it's summarized in this slide. We have seen it already at lesson. This slide here stands only for a summary. Right? Basically it tells that if you have the points, you can extract R and T by an SVD decomposition. Okay? Then to prune once we have but what I wanted to say, what could we do, given that we have potentially a gazillion of correspondences in this set, we could decide how many correspondences do we need to find a solution? In this case, 3, we already said. We could decide, in this case, before doing the expensive part of the algorithm, which is basically trying all verifying the inliers, because verifying the inliers means that I have to scan all the entire point set. Okay? Calculating the solution out of 3 correspondences is a piece of cake. Clear? I want to reduce the number of trials, okay, of large trials. So what could I do is to start selecting, as I said before, triplets of points in the world that make sense, so to say. So if from the first point cloud I pick up, I said I have all with all, I could select a triplet of points, for instance, based on some criteria. Maybe I could pick up the two more distant points on the one cloud and the two more distant points on the other cloud. And maybe the third one, which is orthogonal to the two. I could invent something. The thing is that try to pick up correspondences in a way that the invariants are preserved. Okay? Clear? That I want to simplify it. And then once we have three correspondences and we have the solution given, we could calculate how many of these correspondences are good. How? Well, we calculate the error for each corresponding point pair under the solution. No? We just apply the transform and we see how distant are the points that are said to correspond. If the points that are said to correspond after the transformation are good, we say this is an inlier. Otherwise, it's an outlier. Is that clear? The process? Yes? No? In case of an image, how do you count the inliers? You just project the point, you project it on the image plane, and you figure out how far is the point which you reconstructed after the projection from its actual imaging, from its actual direction. And okay, and then we have a solution. We have a certain number of inliers, and we repeat it, and we repeat it, and we repeat it, and we repeat it. And at every point in time, we pick up the solution that has the most inliers. Okay. Another question that we might ask is how many rounds do we need to have in order to find a solution with reasonable probability? I mean, clearly, there's not a number of trials that guarantee. It depends on the structure of the problem, meaning it depends on the inlier ratio, it depends on the number of points, it depends it depends only on the inlier ratio, actually, and it depends on the minimum number of points required to calculate the solution. So the answer, the question that we are answering now is how many rounds do I need to run ransack on this specific problem in order to have a correct solution with probability at least of x. Is that clear? This is the problem that we want to answer now. Clear, guys? Folks? Now, let's calculate this number of rounds. And it's quite simple. And it's very simple to derive this formula. So let's say W is my inlier ratio. So at least this is the probability that a correspondence is in my input set is good. Okay? Typically for feature-based things, it's around 0.2 or something like that for image business. Let's say that my algorithm to retrieve the solution requires at least n points. So in case of ICP into D would be 2, in case of ICP into D would be 3, in case of projective ICP would be 3, because 3 points are sufficient to resolve projective ICP. In case of image-based things, I need at least 5, or let's say I have a cheap algorithm, so I need 8, and so on. Clear that? And then let's say another variable, what I want to figure out is the number of rounds, is the probability of success, P. Now, what I want to know is how many times do I have to run ransack in order to have at least a probability of 0.99. Now, let's derive it this way. In order to find a correct solution, I need to be lucky n times. So it means that I need the probability of fetching any inliers, given that every time an inlier is picking up an inlier is an independent thing, would be W to the n. Okay? This will be the probability of fetching any inliers. Clear? And typically a number which is much below 0. But then there is a probability of not fetching any inliers, because like if I don't fetch, the probability of not fetching any inliers clearly is the probability of fetching an inlier 1 minus the probability of fetching any inliers. So this is the probability of failing in one run, okay? Because if I fetch points which are bad,
just a thought. In this case, we have to make the hypothesis that the liar ratio remains constant among all the number of trials, right?
yes.
But it is always constant, or there are some applications where the liar ratio may be a little variable among the trials.
I mean, among the trials or within the same ransack run?
Yes, I mean, the idea was that there is the danger that in one iteration we have a certain liar ratio, and then in the following iteration we have a slightly different.
I mean, this is a statistical characterization of the problem, right? So that's a steady analysis that you do. In practice, the inlier ratio changes during the execution of the problem depending on the views. But it does not change within an iteration because an iteration is done with the same data, right? So that's it. It doesn't change during an iteration, but it changes during the evolution. So between different instances of acquisition, in case of images, or so, clearly it will change. But normally you calibrate the thing to the worst case.
Yes, I don't know if I completed the question correctly. Yes, I was being in all the case steps of ransack.
You are an engineer, no? You don't do the bridge for the best case where a man with a bicycle is crossing it over. You do it when 10 trucks are on it. All right. So what I want to say is that okay. So Wn is the probability of success. So 1 minus W to the n is the probability of failing over one iteration. Then I might ask yourself, what is the probability of failing for k iterations? The probability of failing for k iterations is the probability of failing for one iteration to the power of k, because each round in this schema might be independent. That clear? Yes? And so, what is the probability then of failure? The probability of failure, given that we want to have p is the probability of success after k iteration, 1 minus p will be the probability of failure after k iteration. Right? And then, by equating this probability of failure with this probability of failure, which is the same, we could extract k. And how do you do it? Well, guys, this is simple algebra. You just take the log of both things and you have it, and then you highlight k. And so this is the formula that gives us the number of trials required given the probability of success that we want, given the inlier ratio, and given the number of points in the model. You might observe that by changing the number of points in the model, so the minimal number, the number of trials that you require might grow enormously. So if you move from the 5-point algorithm to the 8-point algorithm, well, you might require much more trials to find the correct alignment. Okay, so that's the reason why in the past the people invested a lot of effort in order to figure out a technique that would require less points or less, correspondences to calculate the correct solution. Is that clear? Okay. Now, with this, you would be able to resolve the problem of ICP with unknown correspondences. And you would also be able to figure out, maybe using a smart heuristic for calculating the inliers, or maybe using some feature, because one could extract some invariance on the cloud itself. For instance, the points for which the neighborhood has certain characteristic that would qualify that region of the data to be equivalent to another region of the data. Is that clear? Okay. I think we did one lesson more. I'm quite happy because I was, we might have lost some lesson in the past because, and now the time is ticking, right? So I think that next lesson we will, escape. The next lesson, let me see, lesson plan, no, you know what? Also ransack was planned for today. I had to move it. No, l'ho mosso oggi perché, almeno nel mio lesson plan l'ho mosso oggi. Alright guys, so have fun. And next time we will meet with multi-point registration and multi-pose registration. My goal would be to manage to close by the 17th. Chiudere il corso per il 17. Vi dispiace? Soffrite, eh? So I see people crying.